that makes this interesting. If y is deformation retract of x, then x and y are homotopic, right? And so here's his proof. He says define f going from x to y by f of x equal to big F of x comma 1, and G a mapping from y to x by, well, this is just G of y equals to y for all y and y, so-called inclusion map, right? Iota, yeah. Then if we look at f composed with G, well, f composed with G of y is equal to f of y, which is equal to big F of what? Y comma 1, which is equal to what? Y, right. So f composed with G is literally the identity on y. And then he argues that likewise G composed with f is homotopic to the identity. Let's say this is homotopic to the identity on x by the retraction. So what does this mean? If you put this together with the thing I read, but I didn't write it down, but a corollary to the proposition, of course, is that in this context, the fundamental group of y, right, is equal to the fundamental group of x. So, for example, if you think about, all of R2, for instance, and you think about the origin, or any point, really, you can deform R2 down to the point. You can just shrink it down to the point, So R2 is, the singleton is deformation retract of R2. This also, people will say R2 is contractible. Contractible means that it can be contracted to a point, right? And so then you see why the fundamental group of R2 has to be trivial, right? Because pi 1 rather, of R2 is the same as the fundamental group of a singleton. Well, how many loops can you make in a one-point space? Well, yeah, none. So this gives us new ways of understanding things that we've already proved, of course, because it's easy to prove the fundamental group of R2 is trivial because it's a convex set, But, so I think that's helpful because it expands what you can do with homotopy dramatically as soon as you understand this idea of deforming a space and maintaining the homotopy, right? It's very powerful. All right, so he gives us a list of examples of fundamental groups, which I will write down just to try to cap this discussion off. We are near the end. This is very exciting because I really like what we're doing next. Well, not yet. We still got an hour today, so we're good. Let's see here. So, moving along. So examples, just to recap, the fundamental group of Rn is trivial because Rn is contractible. The fundamental group of the circle is Z, right, as we have talked about in some depth. He says the maps are indexed by their winding number around the sphere. I think he means circle. Then the fundamental group of the punctured disk is also Z. Fundamental group of the punctured disk is also Z by deformation retraction. Oh, so I think we've kind of run into that already, right? If we remove the origin from R2, we also get Z, right? Because if you take, if you think about all of R2, right? And you think about the circle, you can well, you think about all of R2 without the punctured R2, right? I should say. Then you can basically deform all of R2 without the origin to this circle. So the circle is a deformation retract of the punctured plane. We've also seen today that the fundamental group of Sn is 0 for n greater than or equal to 2. And we also saw the fundamental group of the n torus was the n-fold product of Zn. Of Z, rather. This one we haven't shown, but here's another one for you. The fundamental group of Rp2 is actually Z2. And that has to do with that antipodal equivalence that we kind of bumped into, but I can't make that precise in here for you guys, but there's something to learn in grad school. All right, so he then goes on to give some really insightful discussions about connections between, SO3 rotations in 3 dimensions and SU2. He talks about how SU2 is topologically the 3 sphere, and it provides I believe what's called the double cover of SO3. Anyway, so, and then he goes on to talk about spinners and things, which is interesting, but beyond what I've got to say here. What I wanted to get to, jump ahead just a bit here, was his section 3.4 on page 24. So we've talked about the fundamental group, right? So what's beyond that? You can talk about the nth homotopy groups, pi n, of a space, right? What would that be about? He says it's about homotopy classes of maps. He uses, I'll stick with him. He uses an M here, so I'll keep with the M. Maps from the n sphere into the one sphere, not the one sphere, into the space that we're talking about. He says the higher homotopy groups are defined as homotopy classes of maps from Sn into M. He said, however, this formulation is slightly inconvenient. Recall that for the fundamental group, we mapped the identity and demanded the map with equal endpoints. Similarly, you can study maps from S2 to M well, let's see here, for like, so he's describing how to do something a little bit easier for n equals to 2. Let's look at the n equals 2 case. A simplification. So he says it suffices actually, instead of looking at maps from S2, you can trade S2 to M maps for instead things that are from the Cartesian product of the unit interval with itself into M. All right. It suffices, it says, to consider homotopy classes of those kind of maps. And that works because if you take I cross I mod the homotopy equivalence, it is homotopic to, or maybe homeomorphic, I'm not sure, right offhand, to S2. Oh, excuse me, that's not the homotopy equivalence. That is, that's the gluing that we do on the unit sphere to make it homeomorphic to S2. What's that? So if you want to take this unit square, right, and make it into the 2 sphere, what do you do? I think you take all of the edges, right, and identify them together, right? So the equivalence just takes all of those and binds them together as a point, and that gives you the homeomorphism. That quotient is homeomorphic to the 2 sphere. So because of that, I can study maps from the Cartesian, from the unit square into the space and study homotopy classes of such maps. That would be how you would understand. So like these sorts of things would tell me something about like what's the structure of pi 2 of M, right? Pi 1, on the other hand, is based on maps from the 1 sphere. See, because this is, I mean, the same thing is really being done for pi 1. We just, see, because if you have to talk about this, right, and we glue the boundary of that to itself, what do we get? S1, right? So we've looked at maps from the unit interval into the space to understand the fundamental group pi 1. But that would be equivalent to directly studying maps from the circle into the space, right? Because really, pi 1 is all about basically how do circles embed in your space, and can they be deformed to a point or not? So looking at maps from I cross I into the space, it's kind of like blowing bubbles in the space and then seeing if those bubbles get stuck on things. Because if they do, then it's not, you could have bubbles which are not homotopic in some sense. Or if you had S3, you could do I cross I cross I. Because that can, if you can take basically, this story continues. If you take the Cartesian product of I with itself n times, and you identify the boundary as a single point, that is homeomorphic to Sn. And then he has a proposition. He says all higher homotopy groups, pi n of m greater than 1, are abelian. Do you guys know what that means? Good. So the proof is this picture. I don't know if I quite understand it, but it made sense when I read it, but yeah. So he goes on to describe that another thing he mentions in here, which I'll just mention, pi n of Sn, it turns out, is Z. So the thing we saw for the circle continues to be true in that sense. because of higher dimensional analogs of the winding number. It's something about covering spheres that continues to be doable. So I thought that was very interesting. Now this set of notes, part of the reason I really like it, guys, is I once upon a time missed a chance to take a course in mathematical physics that my wife took by a physicist named Sasha Abanov. I think that was his name. And he's a solid state physicist, but his mathematical physics course had homotopy theory in it. And it's like, wait, what? Yeah. So if you go on here and read his section 3.5 on topological defects, he goes on to explain how topology appears in the study of magnetism, how it explains various different phenomena. And, you know, he has physical examples that are tied to various different topological features in various crystals and magnets and so forth. It's very interesting. So you see, for this reason, you can't really study modern theoretical physics without having a pretty good intuition for homotopy and a pretty good working knowledge of the basic examples of homotopy, because they all appear in these rather famous physical examples, which I don't understand this stuff, I'll be honest. Like, I wish I did, but yeah. But that's part of the reason I gave this to you guys, just so you'd see it. Because you'll hear people say stuff like, sometimes I say this, topology is physics. You know, I say topology is charge. Where the charge is where the topology is. Where the charge is where the formulas break down, you know. For the Coulomb field, the place where there's an infinite divergence is the origin, which is where the charge is. It's also where all the non-trivial topology is coming from, the physics. You know, this is not unusual. So this is a book by Mikio Kuga, which I'm sure I'm mispronouncing. It's called Galois Dream. It's a fascinating book. Group theory and differential equations. So you know you're in for an interesting read. And in the middle of this book, there's a story which I will now share with you guys. It's a beautiful story. So here's how it goes. This is from page 77, the 12th week, the universal covering space. When I was a schoolboy, I was seized by the idea that everyone had an invisible tail at his back. This tail was very light, 1,000,000 miles long, very thin, and trails behind as we walk from birth to death. The tail extends far away beyond our world and originates in the land of the dead. When we walk, the tail is reeled out from its source. When we have pulled out the entire tail, we die. The strategy for a long life, therefore, is to try to avoid pulling out your tail. In order to do this, walk null homotopic paths as much as possible. When you return, follow the same route, never go through a tunnel. My ideal world was a universal covering space of the real world, if there is such a thing. My idea completely obsessed me. I was trapped in my own fantasy. I even became to loathe people who crossed the path behind me. And here's a picture of his tail following behind him a little. Yeah, see. It's a delightful book, is it not? Yes. Did I read it to my children? Well, not yet. I mean, in time, when they're ready, after they've had topology, you know, high school. I'm just joking. My kids don't take topology in high school.
Take it in middle school.
In middle school. Anyway, so do you guys have another hour? No, I'm guessing not. So we'll start it next week. Sorry, guys.